Introduction to Polar Coordinates. Objectives. By the end of this lesson, you should be able to graph coordinates and equations on the polar coordinate system, understand the relationship between rectangular and polar coordinates, convert between rectangular and polar. Let's begin our discussion on polar coordinates by first reviewing the Cartesian coordinate system. So if we're given a Euclidean plane, so just a plane in two-dimensional space, using Cartesian or rectangular coordinates, so it's a fancy way of saying graphing functions with x's and y's. So functions like y equals f of x or other non-functions but equations like circles, x squared plus y squared equals r squared, that's just one way of navigating through a Euclidean plane. So Euclidean plane, again, being a two-dimensional plane, we choose to call the horizontal axis x, and we choose to call the vertical axis y. And when we do so, we're actually implying that we're working on a Cartesian coordinate system or a rectangular coordinate system. And to find specific points, we move x units to the right or left, depending on if x is positive or negative. So let's just say we're trying to graph the point 2, 3. So we have learned over the years that the first coordinate corresponds to x, and when x is positive, we know to move that many units to the right on the horizontal axis, and when the y value is positive, we know that's how many units to move up on the vertical axis. So 1, 2, 3. So we know that 2, 3 in rectangular coordinates, or the Cartesian coordinate plane, corresponds to this point right here. But again, this is just one way of navigating through a plane, a two-dimensional space. Another way to do so is using the polar coordinate system. Let's now take a closer look at the polar coordinate system. So certain curves can be more easily expressed using this polar coordinate system, where points now have a different form. So points are still written in these parentheses, but instead of x comma y, we have r comma theta. So r is the directed distance from the pole. So I'm going to stop right there, and on both of these images, I'm going to label the pole. So this horizontal axis and vertical axis, I'm no longer labeling as x and y. I am going to label the origin a special name called the pole, and then theta is the angle made from the polar axis. So this line here that is in blue, which would normally be the positive x-axis, has a special name. It's called the polar axis. So this is on a two-dimensional Euclidean plane. But we typically see polar coordinate systems on graph paper that sort of looks like this, these rings around it. So this line right here is still the polar axis in this case. Actually, I'm gonna erase that and write it off to the right. So this is still called the polar axis. And then this point in the center, the origin, is called the pole. So it's the origin on the xy plane, or the Cartesian coordinate system. On the polar coordinate system, it has a special name, and it's called the pole. So our coordinate points are now formed by thinking about the distance from the pole and the angle made from the polar axis. So I'm just going to go ahead and plot any point on this polar coordinate system. So let's say that one right there corresponds to a particular r and a particular theta. So r as in the distance from the pole. So this straight line distance here, that would be considered r. And because I went from the pole directly to that point, r is considered to be a positive value. And we'll talk more about that when we do some more specific examples. But r is the distance from the pole if I go towards the coordinate point. And then theta is now the angle made from the polar axis. So theta is this angle here. So if I were told the angle and how far out to go from the pole, I can find myself a coordinate point. So that coordinate point is now r comma theta. And so typically what we do is we label on the polar axis units along each of these rings. So the nice thing about using this type of paper to do graphs on polar coordinate systems is we would say, well, this first mark is 1 unit, so this entire ring is 1 unit from the pole, and this next ring is 2 units from the pole. Anywhere, if you're anywhere on the second ring, you are exactly 2 units from the pole. That's like the radius. That's why it's called R. And then 3, 4, etc. So here's what we would not do. We would not put the negative versions on this left side. So we're only concerned with labeling the polar axis and the pole. So if I were to pick a random coordinate point, let's go ahead and say this one right here. Well, if I were to start labeling it, R is how far it is from the pole. So it's 1, 2, 3, 4 units away. So it falls along this fourth ring here. So 4 would be the distance from the pole. And then I would need to find the angle that it makes. So if we remember trigonometry and geometry even, this is a 90-degree angle. This is 0 degrees. And we can see that this portion is split into 3 equal parts. So that means this would be 30 degrees. And this angle here is 60 degrees. So that means this angle, 60, is my theta value. So theta is a Greek letter that stands for an angle. So this coordinate point is 4, 60. So polar coordinates are just another way of locating points on a plane. So not an XY plane, just a plane, so a two-dimensional surface. All right, to make sure we really understand this idea of polar coordinates, we're going to graph the following polar coordinates. So there's 4 different coordinate points here. Let's remember they are of the form r theta. We're going to graph them on this polar coordinate paper. So we have our tick marks labeled on the polar axis. We have our pole labeled. And we're so used to reading coordinate points that are rectangular, so we usually read the first coordinate first and then we read the second coordinate. But with polar coordinates, we're actually going to start with the angle. So for A, I want to go to an angle measure of 30 degrees. So I know that I'm going to be along this ray here, so 30 degrees, and my directed distance r is 2. So the directed distance concept means that I'm going to walk out along the angle 30 degrees towards 30 degrees 2 units. So I'm going to be on this ray and I'm going to go out 2 units, do it in a different color, and mark that point. So that coordinate point there is A. So now let's try with another coordinate point. So we have 3 and then negative pi over 2. So everyone likes degrees better, but unfortunately in math we tend to prefer radians. So a lot of our problems are going to be in radians. In fact, all of them are going to be in radians. So this one is a good example of being able to read radians and just read angle directions. So since our angle is negative pi over 2, negative angles means we go clockwise from 0. So even though this is 3 pi over 2, it's coterminal to negative pi over 2, so these are equivalent angles. So now I know that I'm going to be along this ray here from the pole to negative pi over 2, and because my directed distance is positive 3, I'm going to walk toward my angle of negative pi over 2 and go out to the third ring. And I'm going to fill in that point and then label it the point B. So now moving on to C, we have something different this time. We have a negative directed distance, but we start with the angle. So we're going to go ahead and go to 60 degrees, the ray along 60 degrees. And since I have negative 2 as my directed distance, I no longer want to walk towards 60 degrees. I want to go along the same line, so the ray in the opposite direction, and I want to go 2 in the opposite direction from 60. So I'm going to go 1, 2 out from 60. So I'm still along the same line, but I'm not going towards 60. I'm going away from it in the other direction. So that's what we mean by directed distance. So that is my point C, my polar coordinate C. And to do another example, we have negative 1, 5 pi over 6. So 5 pi over 6 is labeled for us here. A couple things I want to point out. It would not be labeled on the polar coordinate plane. You would label it just as if it was an XY plane. You label your tick marks. Here you label your angles and you label your polar axis yourself. So 5 pi over 6 is right here. So I would normally be walking toward 5 pi over 6, but because my directed distance is negative, going to be along this line, but in the other direction. So I'm going to go 1 the opposite direction to be in quadrant 4, and I'm going to label that point D. Now, there's a lot of different type of polar graph paper. This one only has lines marked at the angles that are 30 degrees apart. But it's possible, I'm just going to create an E. So let's go ahead and say something like, I don't know, to 135 degrees. So 135 is not listed on here. It's between 120 and 150. So it is located here. So it's halfway between these two, 90 and pi, so 90 and 180. So it's halfway between those two at 135, and then I would walk 2 units towards it because my directed distance is positive. So this would be my coordinate point E. So it would be up to me if I was going to use this type of graph paper to label that intermediate ray to make sure that it corresponds to the correct angle. So there's a lot of different possibilities. They don't have to be these nice types of numbers. We can locate any coordinate point as long as we can find the directed distance and the angle. So the angles don't always have to be so nice. Now let's move on to polar equations. Polar equations are graphed by having input that are angles and output that are directed distances. So this is kind of a watered down way of thinking about it, but if I think about functions in terms of x, we substitute in x's and get out y's. So when we think about polar equations, we're going to be inputting angles or into the variable theta, and we're going to be getting out r values that are directed distances. So graph the following polar equations without a calculator. And we have the first polar equation, r equals 4. So the way we can think about this is r of theta equals 4. So for different angles that I substitute in, I am always going to get out a directed distance of 4, positive 4 every time. Doesn't matter what angle I choose. So on this first graph, I'm going to go ahead and label my polar axis. And I'll go ahead and label a couple of different angles. But the unique thing about this graph is it doesn't matter what angle I choose, I'm always going to be a directed distance, so towards that angle of units of positive 4. So if I go towards 0, positive 4 units, I'm right here on the polar axis. If I go towards pi over 6, I'm still going to be positive 4 towards pi over 6. And at pi over 3, I'm going to go positive 4. So it actually doesn't matter where I'm at angle-wise. It doesn't matter what angle I go to. I'm always going to go out 4 units. So every point 4 units away from the pole is going to be part of the graph of this polar equation. So this is actually just a circle. Whoops. So it's going to be kind of hard for me to trace it, but the circle is the graph of this polar equation, r equals 4. So when we started our discussion, we talked about rectangular or Cartesian coordinates and the functions or equations that are necessary to graph certain curves using rectangular or Cartesian coordinates. So to graph this same curve, this circle using Cartesian coordinates, we need the equation x squared plus y squared equals 4 squared, 16, because my radius is 4. So I would need this equation in Cartesian coordinates and rectangular coordinates in order to graph the same function that would arrive by using the polar equation, r equals 4. Or I shouldn't say function, it doesn't pass the vertical line test, but the same curve is graphed by x squared plus y squared equals 16, or the nicer polar equation, r equals 4. A lot shorter, a lot more concise. So that's why polar equations were developed, because for certain curves, it's a lot easier to represent them in terms of polar coordinates than it is Cartesian or rectangular coordinates. Now, r equals 3 sine theta. So now we actually have some angles that we want to try to plug in here, and we'll just go ahead and plug in a few. So we can think of this as r theta equals 3 sine theta, and we can make ourselves a little table. So I'm going to go ahead and do that. I'm going to be substituting in values for theta and getting out values for r. And so let's start with plugging in the nice ones. So 0, pi over 6, pi over 3, pi over 2. So if I substitute in 0, 3 times sine of 0. So sine of 0 is 0. 0 times 3 is 0. So that means that my starting point, so I start at the pole, I go towards the angle 0, but I don't go away from the pole at all because my directed distance is 0. So that means I have a point on the pole. Now, at pi over 6, if I substitute in pi over 6, I'm going to get 3 sine of pi over 6. Sine of pi over 6 is 1/2, so this is 3 times the half. So this is 1.5. So along pi over 6, I'm going to go out 1.5, so halfway between 1 and 2. So it's going to be about right there. And then let's see what happens at pi over 3. So if I plug in pi over 3, I'm going to get 3 sine of pi over 3. So that's 3 times sine of pi over 3 is rad 3 over 2. So 3 times rad 3 over 2 is going to give me approximately 2.598. So at pi over 3, I need to be a little bit more than 2.5. So I'm going to go 1, 2, and I need to be right about there, I would say. So there's a third coordinate point, and then pi over 2. So 3 sine of pi over 2. Sine of pi over 2 is 1, so 3 times 1 gives me 3. So that means at this angle here, I'm going to go out 1, 2, 3 towards it. And then I'm going to cheat and tell you a couple other values. So right here at 2 pi over 3, I'm actually going to be the same value again, 2.598. And then at 5 pi over 6, I'm going to be trying to make it symmetrical because this graph is symmetrical. It's going to be right here at the same value at 1.5 toward 5 pi over 6. So this is at 2 pi over 3. This is at 5 pi over 6. So it's actually going to look like this. It's supposed to be a circle. So it's not centered at the origin, and it takes a little bit more effort because we're plugging in all these different angles. So for some cases, it's going to be easier to graph by hand. For other cases like this, we're actually going to use our calculator, and we're going to need to change our calculator to polar mode. So we're going to move on to that topic next. We're going to move on to graphing polar equations with the calculator now. So the first one we're going to graph is r equals 1 plus 2 cosine theta. And before we enter in our equation, we're going to have to change our mode over to polar. So choose mode. Right now it's probably highlighted under function, so you're going to move it over and highlight POL for polar. And then you can go ahead and go to y equals, so that you have now r1, r2 instead of y1, y2, etc. So we're going to enter our expression. I've already entered it. It's 1 plus 2 cosine theta. That's our polar equation. And the first thing I'm going to do is just graph it in the standard viewing window. So I'm just going to go to zoom 6. Oh, there you go. So there is the graph, but it's not very clearly detailed, and we didn't see how it was graphed. So I actually want to change the viewing window. So I'm going to make it a little smaller. And I want to go over the window in general, because you'll notice something that's new. When you click window, typically the first thing you saw was x min, x max, but now you're going to see this theta min, theta max. So that's because the input variable is an angle. We are substituting in thetas to get out r's. Now, in order to see a complete graph, we're going to want to plug in everything from 0 to 2 pi. That's the entire unit circle. So you'll notice by default, that's what the calculator is inputting. So theta min is 0, so that's the smallest angle in radians. So you want everything in radians, radian mode. So theta min is 0. Theta max, the biggest you're going to plug in is 2 pi, because that's going all the way around. So that'll give you a nice and complete graph. So notice 2 pi is 6.28, etc., because pi is 3.14. So we're multiplying it by 2. So that's already in there by default. And then my theta step size, that's how many different theta values it's going through. So every 0.130896, it's going to go up by that amount every time. So how we decided in that previous example, I was going to plug in 0, then pi over 6, then pi over 3. My theta step there was pi over 6. My theta step here, this actually translates to pi over 24. So it's plugging in 1/24 of 2 pi every single time. So then after the theta values, then that's when we get to x min and x max. So I want to go ahead and change the smallest x value to -1, the biggest x value to 4. We'll leave our x scale as 1. My y min, I don't fully remember, but let's just say -3, I think, to 3 will do it, so that we have a pretty blown up graph on the screen so that we can see it pretty clearly right now. So now I'm going to go ahead and hit graph. Whoop. And hopefully you saw right now it graphed the function and where it started at. So if we were to trace this function right now, which we are about to do, we're going to graph this function onto our little polar graph paper. I want to also do something that indicates the direction that the graph was drawn in. So I'm going to go ahead and regraph the function so we can just pay closer attention to it graphing. So to regraph the function, to show it draw it again, I'm going to go to second program for draw, that's right above program, and I'm going to choose 1 for clear draw. So there I went ahead and drew it again. So it started over here because our polar equations, we're starting by plugging in 0 first. So the graph starts out up here and then it makes the turn to make the inner loop, and then it's going to go all the way around where it meets back up again at 0. So I'm going to go ahead and draw that graph. So let's see, 1, 2, 3. So it starts out over at 3, and then notice it goes through 1 and -1 on the vertical axis. So I'm going to try to draw it as accurately as I can right here. So here we have 1, 2, 3 tick marks over. That's where my graph begins. And then it's going to go through this point, and there's 1. So it's going to go around, and it's going to make a little inner loop. Whoops, that's not perfect. And it's going to look something like this. But what I'm going to do is I'm going to draw a direction arrow. So I'm going to label this point as my starting point, and it follows this path here all the way around until it gets back to where it started again. And the reason I'm going to do that is because pretty soon we're going to be finding the area within these polar curves, and it's important to try to understand where you're starting at. So since we start plugging in angles, we're starting at an angle of 0, and then we're moving in this counterclockwise direction, and it's nice if we can follow or trace the path that the curve has taken as we increase the angle measure from 0 to 2 pi. So here's the graph. It's definitely not perfect, but it's really hard for me to draw on this little tablet. Perfect, nice curves. So now let's go ahead and move on to the second polar equation. So 3 sine 2 theta. So let's go ahead and enter that one. So 3 sine 2 theta. And then we'll go ahead and graph it in the same window, see what happens. So we're a little bit off here. So we'll go ahead and change the viewing window. So I'm going to go ahead and change my x min, let's say, to -4, and I think that'll show just enough. Alright, so notice what we have here is we have what looks like a flower, and there's actually a special name for these types of polar curves. You don't have to concern yourself with it, but just in case you were wondering, it is called a rose curve because it does look like a flower. And the reason that there's an even number of petals in this flower is because the function is sine 2 theta. So there's going to be 2 n petals when this number is even, and when this number is odd right here next to theta, then there's going to be exactly that many petals in this flower. So again, you would be able to graph this on your calculator. You wouldn't need to know that, but just some fun facts about polar equations, that they do look kind of cool, and we would have a really hard time trying to come up with a rectangular equation that would graph this type of function. So here, let's see, the distance that we're from the origin actually happens to be the number in front of this equation. So 3 is the directed distance to the furthest point on the petal. And let's go ahead and just draw the general shape, and then we'll go back and think about how it was drawn. So it looks something like this, 3 units away. It's going to have a hard time doing this. And 3 units away here, and 3 units, nope, did I miss? Yeah. And 3 units away here. So it looks something like this, but now let's try to go back in and think about where it started. So let's redraw it. So we'll go to second draw, and then 1 for clear draw. So it started with this petal right here. So we can go ahead and label. It started at the origin actually, so that's where it started, and then it proceeded to move in this direction. So it heads over here first. So I'm going to label that as 1. So that was the initial direction that it headed, and then I already forgot, so I'm going to hit redraw again. So here it goes in this direction, and then it goes down here in this direction, and then it goes over here. So let's just second draw one more time. So it goes around, around, and then it ends up in quadrant 2. So let's go ahead and try to trace that out. So then it went down here, and that was second, and then it kept going over here, and that was third, and then it finished off in quadrant 2, which is fourth. So just to give yourself a little bit of an idea of what's going on, some of the problems that we're going to be solving coming up are how to find the area in one of the petals of a particular rose curve of this form. So it's helpful to determine the order that the petals were drawn and constructed based on plugging in the angles from 0 to 2 pi. Now let's look at the relationship between rectangular and polar coordinates so we can convert back and forth between the two. So to go from polar to rectangular is the easier direction. If I have a polar coordinate of the form r theta, to get to x's and y's in rectangular form, x is just going to be r, the directed distance, times cosine of the angle, and y is the directed distance r times sine of the angle. And this should strike you as familiar. In trigonometry, we do think of cosine as the x values and sine as the y values. So polar to rectangular, easy. Rectangular to polar takes a little bit more effort. Rectangular meaning we start with x's and y's, and then we're trying to find that directed distance, and we're trying to find that angle. Well, the directed distance, this is actually a modification of the distance formula, and we're going to need to figure out, so we can plug the x and y into this square root of x squared plus y squared, but we're going to need to determine the directed distance portion, the directed portion. So we're going to need to decide if the directed distance is plus or minus, and that all depends on the angle. So to find the angle, tan inverse needs to be used. So tan inverse of y over x will give us our angle, and then we need to be the ones to determine the correct sign for r based on the quadrant that xy fell in and the angle that comes out of using tan inverse. So we'll do some examples of these next, but these are the relationships that allow us to go from rectangular to polar and polar to rectangular. Alright, convert between rectangular and polar coordinates. So this is a polar coordinate that I've been given. So here's my r and here's my theta. And then these second two examples, these are x's and y's. So I should have written that out, but I'm telling you that now. So r theta is my polar coordinate, so 2, 5 over 6. So if I want to get to rectangular, this is the easy direction. So here I'm going to have 2 cosine of 5 pi over 6. And then 2 sine of 5 pi over 6. And I would actually want to evaluate this. So it would be 2 times cosine 5 pi over 6. So 5 pi over 6 is in quadrant 2, where cosine is negative. So it's going to be times negative cosine of pi over 6, which is radical 3 over 2. So that's the x-coordinate. And the y-coordinate is 2 times sine of 5 pi over 6. So 5 pi over 6 again in quadrant 2 where sine is positive, and sine of pi over 6 is a half. So simplified, this is negative rad 3, comma 1. So here is my coordinate point written in rectangular. So there's my x and there's my y. Alright, so now let's figure out how to get from rectangular to polar. So I can't just do this direct this equals this quite yet. So I have to do some scratch work. So the directed distance portion, so r is either going to be plus or minus, so we need to make a decision on that. I'll put a question mark. And then x squared, so 3 squared plus negative 3 squared. So 3 squared plus negative 3 squared, that's 9 plus 9, so this is radical 18, which simplifies to 3 radical 2, because 18 is 9 times 2, radical 9 is 3. So my r is either plus or minus, so I'll just do that, plus or minus 3 radical 2. So we have to decide that, and we're going to decide that when we figure out the angle. So the angle is going to be tan inverse of y over x, so negative 3 over 3, and tan inverse of negative 1. So this goes back to a little bit of pre-cal. What do you have to plug into tan to get out a negative 1? The answer to this is negative pi over 4. So negative pi over 4 is the solution to tan inverse of negative 1. So now let's think about this coordinate point on the xy plane, 3, negative 3. Where's that? So 3, negative 3, that's the coordinate point we're trying to write as our polar coordinate. So negative pi over 4 is the angle. So negative pi over 4 meaning we go in a clockwise direction. So this is negative pi over 4. And then r is the distance. So if I am going down to negative pi over 4, I want to go towards negative pi over 4. So I want to choose the positive directed distance here. So my polar coordinate is positive radical 3 over 2. And the angle is negative pi over 4. Now, I don't want to say this is the one and only solution because polar coordinates have more than one way we can represent them, because angles don't have unique representations. There's infinitely many coterminal angles. So another way we could write this is 3 radical 2, and then instead of negative pi over 4, we could write this as 7 pi over 4, because that's the same as going in the counterclockwise direction, 7 pi over 4. So either of these and many other versions of this are answers to an equivalent polar coordinate to 3, negative 3. And then finally, let's go ahead and take a look at 0, negative 2. So before I even start using this formula, I'm actually going to draw a picture of where 0, negative 2 is on an xy plane. So 0 means I don't go anywhere on the x-axis. Negative 2 means I go down on the y-axis. So I'm trying to represent this coordinate point using polar coordinates. So this is actually probably easier to do without using this formula mess, because this angle down here is 3 pi over 2, or negative pi over 2. Depends on how you look at it. And then you're going 2 units towards 3 pi over 2. So we can just jump straight to 3 pi over 2 as representing this rectangular coordinate in polar coordinates. Or again, 2 negative pi over 2 is another option. And just to throw out a third option, I can also say that it's pi over 2, but now I'm going in the opposite direction. So my directed distance would be negative 2 if I chose pi over 2 as my angle. So remember, I go towards the angle if the directed distance is positive, but if the directed distance is negative, now I'm going the other direction. So there's 3 different ways that I've shown for representing this rectangular coordinate as a polar coordinate. So this is one of the options, here are the other 2, and then here were 2 different options for the second example. The last thing we're going to do is convert equations between rectangular and polar. So the first one, we're going to go from a rectangular equation to a polar equation. So we have y equals 2x plus 1. So we have a linear function in terms of x and y. And we want to turn everything into r's and theta. So let's remember our relationship that x equals r cosine theta and y equals r sine theta. So those are the 2 substitutions we're automatically going to make so that we have everything in terms of r and theta. So y is r sine theta, and then it's going to be 2 times my x is going to be r cosine theta, and then plus 1. So right now this is an equation that is in polar form, but ideally we would like to solve it so that it's r equals a function of theta. So now what I'm about to do is I'm going to go ahead and gather all the terms with r on one side. So I have r sine theta already on the left. I'm going to subtract 2r cosine theta. So this quantity that was on the right, I subtracted it to the left, and that's going to equal 1. And now that everything with r's is on one side, I could factor out an r, and I have sine theta minus 2 cosine theta equals 1. And so now finally I can get r by itself by dividing by this entire expression. So I get r equals 1 over sine theta minus 2 cosine theta. And if we wanted to double check that we did it correctly, we know what 2x plus 1 looks like. We know it looks like a linear function with a slope of positive 1. So let's go ahead and graph our polar equation that's solved for r. So we'll go ahead and clear this out, make sure and enter it correctly. So it's 1 divided by the quantity, and we have sine theta, and it's minus 2 cosine theta. And we'll go ahead and hit graph. So notice it ran through that line a couple times. It's a thick, darkened line, but it is the correct line. So I have a y-intercept of positive 1, and then I have a slope of positive 2. So this is the correct way to express y equals 2x plus 1 as a polar equation. Finally, the last example, convert the following equation from polar to rectangular. Now this one is a little bit different. It's a little bit trickier to see how exactly we're going to eliminate the r's and the thetas and turn them into x's and y's. So let's write down what we know. We know that x equals r cosine theta. We know that y equals r sine theta. So one of the things we can do, and there are many different ways we can solve this problem, but right now I have a cosine theta that I can replace with at least something to do with x's if I rewrite x equals r cosine theta as x divided by r equals cosine theta. So now what I have is a replacement for cosine theta that at least has an x in it. So I have r equals 2, and I'm going to replace my cosine with x over r. And so now what I'm going to do is I'm going to multiply both sides by r. So if I multiply both sides by r, the left side is r squared and the right side is 2x. So I've eliminated my cosine theta, and now I have this r squared here. And what we had previously was that r squared equals x squared plus y squared, and what that comes from is the fact that r equals plus or minus radical x squared plus y squared. So it's really the Pythagorean theorem. So if r squared is x squared plus y squared, that means I can replace the left side with x squared plus y squared equals 2x. So now this equation is entirely in terms of the variables x and y, so it's considered a rectangular equation. There's not going to be a way that I can turn this into just one function. So if I try to solve this for y, I get y squared equals 2x minus x squared. And I'd have to take the square root of both sides, so I would get plus or minus the square root of 2x minus x squared. So this is actually going to be a conic section that we have here, and it's not written as just a single function. It's not actually going to be a function at all. It's not going to pass the vertical line test, but it is a rectangular equation as far as everything is in terms of x and y. So this is one way to express it, or this is another way to express it. But it took a little bit of manipulation from the formulas that we had that converted between polar and rectangular.